If fire was humanity's introduction to mastering energy, fusion is its culmination. Our increasing demand for energy, which continues to grow with technologies like AI, has outpaced the capabilities of our global energy system. We cannot grow, progress, and decarbonize without a new path. We need a new power source. Fusion energy has the capability to be one of the most valuable technology sets in history. Said simply, fusion is our opportunity to decouple energy production from resource consumption. The prospect has sparked a global race to commercialize fusion, and the winner will garner massive international power. Scientists at the National Ignition Facility proved fusion is possible. Now it's our job to successfully scale it to commercialization.
Your trusted source for information on the energy transition. This is the Insider's Guide to Energy podcast. Welcome to another edition of the Insider's Guide to Energy. I'm your host, Chris Sass. With me is the co-host, Jeff McCauley. And this week we are talking fusion. We have Scott Mercer with us. Scott, welcome to the podcast.
Thank you, Chris. Appreciate it.
Well, I've tipped our hand a little bit to our audience. We're going to talk about fusion. What fusion company are you a part of and what's your role?
Yeah. So I am the CEO of Focused Energy.
Okay, so you're CEO of Focused Energy. What exactly is Focused Energy?
So Focused Energy is a laser fusion company that is working on bringing forward kind of large-scale fusion power plants based on really a similar architectural configuration to the system that has seen energy gain, which is the system at NIF in Livermore, California.
Now, what is the impact? We've done quite a bit of fusion content. We really enjoy talking about fusion. It's always a little bit of an easier topic because it seems rather futuristic and farther away, whether someone says 10 years or 30 years, depends on who you're talking to. What's the impact and why is fusion so important for energy transition? I mean, you and I were having a conversation earlier today and we were talking about having all kinds of energy available. What's the importance of fusion?
You know, from my standpoint, fusion is really the culmination of all of these efforts. I mean, fusion is really functionally how the universe itself creates energy. And so when I think about fusion, I think about that as the culmination of humanity's energy journey. Like, it is our ability to move from using resource consumption to create energy to using sort of fusion adjacent things like wind or solar to create energy to kind of getting energy directly in the same way that the universe creates it. So the fact that we are getting close to that we've seen that in experiments like at NIF is pretty exciting.
Scott, I don't know much about fusion either, but the limited knowledge I have is that there are two main approaches, one with lasers and one with magnets. What are we trying to do? And tell us about the laser-based approach that you're working on.
Yeah. So, fusion is kind of a core physics principle. There are a lot of different ways to achieve fusion. There are really only two approaches that have been studied with significant investment and depth over the last half a century. So you have laser fusion, which is what Focused Energy is working on, which was primarily funded by defense programs and has been done behind the fence, mostly by the US government and by governments really as they work on weapons programs. And then you have magnetic fusion, which has been more an external facing scientific community program. Doesn't have as many applications from a military perspective, but is also a big energy focused program. From the sort of standpoint of big fusion moments, NIF, which is the program that's going at Lawrence Livermore, achieved energy gain for the first time in fusion back in 2022, which means more energy out of a fusion experiment than was put in. And that's been quite a landmark experiment for the community. So from our standpoint, what we're looking at is how do you take that NIF event, that gain event, and that sort of sequence of growth of energy output from the fusion targets and start to really look at how you might do that from the lens of a energy generation program rather than a weapons simulation program.
That's great. One more semi-technical question. How do lasers force something together. Most people think about lasers as not interacting with matter. So what different kind of laser or different kind of matter is this that you're able to push things together with lasers?
So the easiest fuel to fuse from the scientific community's perspective is a combination of isotopes of heavy hydrogen, so deuterium and tritium. From a laser fusion perspective, what we're doing is we're building very small targets, essentially little pearls of deuterium tritium that are encased in a polymer shell and that are then hit with laser energy spherically from all sides to essentially ablate off the surface of that shell and create a spherical inward-facing rocket engine. It propels the deuterium tritium towards the center of the target. A little 4 millimeter target collapses to about the diameter of a human hair. And at that point, you can spark a fusion reaction.
Got it. So the lasers are kind of lighting the fuse, and then this sort of very hot spherical flame is what pushes them together.
Yeah. I mean, the best way from my perspective to envision this is as a cleanly fueled, very scientifically sophisticated combustion engine, sort of like the single cylinder of a car engine. So you inject a small amount of fuel, in our case, one of these little tiny targets. You compress it, not with pistons, but with laser energy. You spark it, also with laser energy. And then that target releases a massive amount of energy, becomes the hottest point in the solar system at that moment in time. That energy dissipates towards the walls of the chamber and is then picked up as heat and as neutrons. And that heat's transferred into steam and eventually into electricity.
So the difference here, though, is you don't need to maintain that state. You're continually creating a fusion state, but you're not trying to maintain a state and keep a stable state.
And, I think that what I've seen from a perception challenge perspective is that there is, from some members of the community, this idea or this thought that magnetic fusion seems simpler than laser fusion because the idea of injecting these little targets at 10 times a second, which is what we inject them at, sounds very challenging to people. The difference is that in magnetic fusion, you have this steady state device that has to keep that deuterium tritium hovering. For us, that 10 times per second injection of those little targets is, to the combustion engine analogy, sort of like a gasoline powered car at idle running at 600 RPM. Like as a mechanical device, it's quite simple. And from a laser perspective, lasers and the physics of the experiments for us act on very, very small minutiae of a second. So the device is mostly waiting for a new target to be injected from the laser's point of view.
What kind of energy does a laser like that take to get the strength you need or the quality you need to start a fusion reaction?
So these are very high energy lasers. We are using essentially large bundles of kilojoule lasers. So about 1,000 to 1,500 of them, depending on the facility, that are bundled together into a spherical target chamber. So think about a 10-meter wide ball with spherically arranged ports on each side so that you can hit that little tiny target with laser energy in a perfectly symmetrical way from all edges.
And when this is commercialized, if I'm doing gigawatt production or larger scale energy production, how big are these arrays of lasers that we need to do that?
So for that scale, we think about right now, our facility scale is right now conditioned on the thermal management of the energy that comes out of the target. So that target, when it's ignited, is about 150 million degrees. It's very, very small. So at the point that it reaches the walls of that 10-meter chamber, that energy dissipates to less than 1,000 degrees and is a much, much more manageable amount of heat for material science reasons. And what we're looking at is really taking off-the-shelf lasers that we can build, not off-the-shelf at this point, but that we can manufacture on a manufacturing line at scale, and combining them into these larger laser arrays so that we can get about a gigawatt of power out of each individual fusion reactor. And that's wall plug gain or engineering gain. So it's about 2 gigawatts of fusion energy output from those targets.
Scott, tell us a little bit about the timeline of when you see this reaching various milestones, and what are the biggest technical challenges between now and those milestones?
So I think that at this point, there is sort of this breadth of approaches to fusion. There's 45 companies in the space and growing, probably higher than that now. But everyone has a different pathway towards really a combined focus to get fusion programs up and running in the 2030s. From our standpoint, this is a somewhat unique project in that focused energy is the closest system architecture to what's been worked on at NIF, which means that we are really following the only fusion program that has ever achieved energy gain. It's one of the biggest scientific milestones that one would need to prove in order to move towards fusion commercialization. So when we think about the timeline for us, we think about really a set of engineering and supply chain problems rather than this binary question of, if you use our approach, will it fuse? We know it will fuse. We know it will produce gain. So I am now looking at building a integrated engineering facility to try to do these fusion target injection, target ignition simulated sequences over the next 4 or 5 years towards the idea of that first pilot plant coming on in the mid 2030s and rapid commercial deployment thereafter. The focus for us, and I think you'll hear this from a number of further along fusion companies, is not necessarily on building that pilot plant. It's on really setting the ground to build that first generation of commercially viable reactors.
What is the supply chain like today for the materials? So you mentioned kind of off the shelf lasers, and I'm sure these high power lasers are just ready to be built at scale, sarcastically. Describe the supply chain for your vision. So 2035, what needs to be in place for all this to be deployed where we start seeing this deploy at scale?
So broadly, from a supply chain perspective, we can think about, at its core, there are 2 core technologies that Focus Energy is working through. It is the fusion fuel targets, and we have a targetry lab in Darmstadt, Germany, that builds these targets that interact with the laser beams, laser energy. And then it is these high energy, high repetition rate lasers. These lasers right now, they exist. We've actually have one that is built with our IP that exists in Europe. Similar lasers exist in scientific programs worldwide, but you can think of them more as built like a satellite right now, where these are built for generally a government client. They're built one at a time. They're very bespoke. If you take NIF as an example, they built the entire supply chain just for that program, the laser glass manufacturing, the laser manufacturing themselves, only built for that program and down to the factories, and then shut down after that program was complete. So what we really need to do from a focused energy perspective is to take a piece of highly technical equipment that's built like a satellite, kind of one at a time, big budget and individually bespoke, and move it to something that's built like a car, on a supply chain, in a factory, repeatably at high volume. And that becomes really the big supply chain question from a laser fusion perspective.
But with so many versions of what fusion's going to be, like you're making a calculated bet based on your conversation, like that you said, hey, our technology's already been proven-ish. They're getting positive energy gain out of it, where others haven't shown that yet. So we feel like we have a hedge here, that we're on the right direction. But you need the supply chain vendors to buy in, and you need to be the leading indicator, right? So I look at Commonwealth Fusion and others that have raised, a few $1 billion, but they'll admit clearly they need a lot more money to get to a commercial rollout. I mean, that's a small number in the whole scheme of things. How do you spark the supply chain in the direction of lasers or in the optics or whatever it is that you need, as opposed to magnets or Tokamak or whatever technology others are betting on?
I mean, they are different but concurrent supply chains. So we can see these different programs, depending on what else might work or might see gain in fusion. You could see a world in which several different, macroeconomic fusion programs unfurl over the last 10 or 20 years alongside each other. And frankly, from an energy demand perspective, that's probably the best case scenario. We would love to see several different sort of high potential energy sources in the nuclear space that are all sufficiently viable that you can build supply chains as quickly as possible to deploy this as quickly as possible. Because frankly, the energy gap that we see as we look towards 2050 and beyond is quite profound. So from my standpoint, the laser fusion supply chain is really something that's working in conjunction with the development of these laser diodes that allow for high repetition rate lasers, and in conjunction with a lot of the laser-based weapons work that's happening in the Defense Department that has really pushed the supply chains forward over the last 5 to 10 years. It is a small percentage. I think that there's a number of material science and energy harvesting kind of components. The idea of the tritium breeding, et cetera, that can be somewhat similar. But I think we're still somewhat early days in the development of some of those technology sets. And as you get a little bit more and more sophisticated, they're probably adjacent more than they are shared.
Right. So one of the things that's really interesting from the start that you differentiated is that magnetic confinement has evolved due to it being more public. Mm-hmm. And really the laser-based approach didn't progress as quickly because of its association with military applications. Fission technology has been limited due to potential for proliferation of nuclear weapons. Does proliferation of laser-based fusion systems have some of the same risks?
Well, so from a fusion perspective, it's interesting because magnetic fusion arguably is not further along than laser fusion. It is only further along in public perception. Laser fusion has achieved more of the sort of proof points that are needed to move towards commercialization. It has fewer scientific showstoppers on the go forward than magnetic fusion still has to overcome. So from our standpoint, really, it's getting across the clear engineering pathway for laser fusion and showing that really from a technology perspective, and really given that we've seen gain from a NIF standpoint, laser fusion is the furthest ahead technology set in the space. As to kind of radioactivity and proliferation and some of these things that are problematic from a fission perspective, laser fusion has very few of these. The laser technology that we're using from a defense perspective is not really adjacent to what's happening in the weapons program, aside from the fact that it uses similar components. You couldn't turn a fusion laser into a weapon, I guess is the way that I would say it. And really from a radioactivity perspective, we use very, very small amounts of tritium, which is a short-lived radioactive material, which means that our industry is regulated more like a medical facility that does x-rays than like a fission power plant might be. And that's been a big shift over the last couple of years as governments start to put regulation in place, preparing for the commercialization of fusion power.
You've taken us through a bit of the journey and the technology, but you're not a physicist by training, I don't believe.
I am not.
How did you end up becoming the CEO of a fusion company? Because I don't think your background, like I said, is physics.
So, yeah, from my standpoint, my entire career has been focused on energy transition. And from my standpoint, when I was in college, I really looked at this idea that across our working careers, we have the opportunity to build a truly generative energy system, to move from resource consumption as the core of our energy generation capacity to moving beyond that. I started out with the idea of building electric car charging in 2010. Essentially, how do you build electric car chargers 15 years before you might see mass adoption in a way that could make money from day zero and act as a social psychology tool to signal people that EVs were here and that it might be interesting for them to consider the cars. Took that business from scratch to IPO in August of 2021, which was the same month that NIF reached ignition. And when I saw NIF reach ignition, I realized that commercial fusion might be on a similar trajectory, where that might be the opportunity for the investment market to start to take fusion quite seriously. So I started looking at this really first from an investor lens. How would you build an investment portfolio of actual deployable operational fusion programs? And was approached by the team here, which is a very, very strong scientific pedigreed team, to look at being an operator with the company.
Doesn't it take considerably longer? You talked about a 4 or 5 year cycle of building expensive equipment to go prove and vet this out. So it's a different economy of scale, and that you would need really patient capital, or you'd need federal dollars or something, because you need a tremendous amount of capital to do what you're talking about, don't you?
Well, one of the fun things about the space is that I can truly look people in the eye, whether there's investors or governments or sort of people joining the company, and say that this technology set can make one of the most valuable industries the world has ever seen. And the companies that win here will be some of the most valuable companies in the history of the world. So yes, it is a different scale of capital, but it's also a different scale of return. Companies that have the capacity to master technology sets like this do have a relatively uncharted upside, I would say. That's kind of the big picture story. In the small picture story, we are a fairly pragmatic company as it comes to supply chain and technology capacity. We have this laboratory that's one of the best in the world for laser particle interaction experiments that supplies these little targets, not just for fusion experiments, but for other laser particle interaction experiments worldwide. And we also have some high energy laser IP that the company has developed that's been quite interesting to other laser programs scientifically or in the fusion community. So it is quite likely that Focus Energy will sell the components of our technology stack before we actually start to sell integrated fusion reactors. And we've gotten significant demand on that side as well.
Yeah, Scott, just on that, who are the customers for those lasers? And love the parallel, obviously, of the 15-year journey with something that can make money from day zero.
Well, so maybe the most interesting application for the expertise of the company, Focus Energy really started out of Darmstadt, Germany, out of the university in Darmstadt, and was this targetry lab building particle physics targets for laser experiments. There were two core applications. One is fusion targets, and the other is this imaging system where you can use lasers to shoot at particles, essentially a leaf of water. You shoot the laser beam through that leaf of water, and it shoots out very consistent beams of neutrons and hard X-rays. If you put a detector on the other side of a piece of infrastructure, you can get an image of not only what that piece of infrastructure looks like inside, but also a material assay of what it's precisely made out of. It happens that one of the most interesting customers for that set is the current fission industry. And we took one of our first near-term revenue contracts with RWE, a nuclear energy operator in Germany, to take a contract to install one of these systems on site at a decommissioned fission power plant to help them assay all of the radioactive material that they have from their past fission regime as they prepare for the future. Yeah. So just in the general history of the company, Focus Energy was started in Germany by a well-known professor in Darmstadt, Professor Marcus Roth, and Thomas Forner. The two founders of the company started the company based off this targetry lab, then went out and acquired the IP for a high energy laser company in Texas, then went to the scientific leadership team at the National Ignition Facility, the team that had led the ignition program, showed them the white paper for the company, and essentially hired the majority of the leadership team from NIF once they had seen gain to come to Focus Energy and work on energy production from laser fusion. I think that the idea of achieving scientific gain is a very exciting thing from a scientific community perspective. But if one has the opportunity to work on atomic weapons or to work on an energy source that could change really the future of humanity, it's not necessarily a difficult choice for some people to come across.
I have a very rudimentary question, or probably a silly question. I asked it in the chat to Jeff earlier in the interview. When you're talking about this, if we're going to go do deep space exploration, we probably need fusion energy, I would assume, from stuff I've heard or seen. Is there a preference for laser or magnet for the space program? Or do they lean one way or the other of what they're hoping gets developed, which would be easier for deep space travel?
I think from a space travel perspective, you start to get a little bit more speculative and your system requirements change quite a bit. So when I think about fusion and I think about kind of all of the different approaches that we might discover, all of the different sort of capabilities that we might master, it becomes wider as you get kind of further afield. But when you wind it back to what we need to do today, that's when it really focuses on these larger scale baseload replacement power plants, where really, from my perspective, and it's a fairly aggressive perspective for the fusion community, but there's only one fuel source that makes sense, which is deuterium tritium. And there are really only two technology sets that make sense as a simple bet, which is magnetic fusion or laser fusion. So there's lots of different programs going on, but those are really the bets that I think can be made from a commercialization perspective.
So I agree with you that it's transformative to mankind to have fusion, or I don't know if you said that in your words, but I tend to think that when and if we get to fusion, that it would be. I guess one of the naysayer kind of near-term things is we're competing for keeping global warming and greenhouse gases down, and there's only so much capital being placed. And so does it make sense to bet on a future technology, or should we be doubling down near term for the renewables we know can impact global change immediately, and then make a little bit longer term bet on fusion? What's your, when you hear something like that? I mean, I've heard this many times. What is your response?
So when we think about kind of the goal sets over the next 20 years, a lot of people talk about 2050 as kind of the marker from a decarbonization perspective, from an energy perspective. And the stories that we tell currently don't add up very well. As an example, the US EIA projects energy demand based on a base case scenario, a high growth, high economic growth scenario, and a low economic growth scenario. In the high economic growth scenario, the projection is that by 2050, we consume 19% more coal than we consume today on a global perspective. So when we talk about the larger kind of political will to decarbonize, the larger political laws to decarbonize, the drumbeat decarbonize to net zero versus the realities of what the energy projections are going forward, you realize that gap is very, very wide. And it is much wider than the larger community is really willing to talk about in public, to my view. So the answer is absolutely all of the above. It is that we do have to push very hard on renewables. We will, unfortunately, have to make our peace with the fact that it will be incredibly difficult to wean ourselves off fossil fuels. And we have to make the push very hard to figure out novel technology sets that will allow that to happen. It is not a simple thing to do. It is nowhere near as simple as it is talked about from a political perspective.
Yeah, Scott, I tend to agree. We need everything possible. we haven't even talked about the energy requirements for carbon removal, which blow whatever energy needs out of the water with everything we can as fast as we can build it. I have a similar question, which is just Commonwealth Fusion raised $2 billion. We've said that a couple times. Are there enough investors with a 10 to 15 year time horizon that can put in the billions of dollars you need on top of the government sponsored collaborations?
Yeah. So when I think about the program for us from here, I think that there is this idea that you have to fund fusion with equity investors going forward for a very long time horizon. I think the general story that I hear from that people kind of think about at this point is this idea that you're going to take a bunch of scientists and engineers, they're going to go away for a decade, they're going to build a big shiny machine, they're going to flip the switch, and we're going to see if it turns on and changes the world or if it makes a little fizzle noise and shuts itself back off. And really, from a laser fusion perspective, in a post-NIF world, that's not the case. So from our standpoint, what we need to go out and prove is not that the machine can actually see game. It's really that you can build the supply chains and the engineering integration to do this repeatably and at a commercially competent LCOE, a levelized cost of energy. Which means that when I think about my timelines, I think about working backwards from a commercial deployment of those first of a kind reactors starting in the late 2030s. And that functionally means that I need to have my commercial energy partners signed up for fusion commitments by the end of this decade. So to go to investors and say, look, what we want to do is build about $100 billion worth of a pipeline to fusion reactors over the next 4 to 5 years. We want to de-risk all of the engineering challenges left existent as quickly as possible. And we want to build the supply chain story behind that to make sure that we can actually meet those orders. You have a very, very different business story. And that's the business story that we're out in the market telling. So from an investor time horizon, yes, it is 10 years till the pilot plant comes on, but it's more like 5 years until you have that visibility to that first $100 billion in orders to our view.
Now, with all the challenges in the world right now with Middle East oil prices and Europe energy prices, gas has been crazy. Your European American partnership, your transatlantic, and a lot of energy is politics. It's always politics and energy. How does that? I mean, in the beautiful world where we get free energy and we're just like the sun and we make everything go great. That sounds really good. But how does that work in reality? So you want to get $100 billion worth of projects off the ground, but you're working in 2 different economic zones. You're in North America and in Europe. How does that? Is that a headwind for you, or is that a tailwind? Describe how that helps or hurts you.
Yeah. So when I think about the deployment of fusion, I think about it from a global construct. Right. The ownership of the IP, the ownership of the supply chains might be more localized. The deployment is global. And it's an opportunity for the countries that lead the development of these fusion technologies to be a global supplier of baseload energy going forward. We are taking the entire supply chain of the carbon economy and replacing it with the supply chain of the fusion economy, which is much more about technology development and science than it is about resource extraction. So the opportunity for countries to really build that development and supply chain ecosystem is quite profound. From a focused energy perspective on the transatlantic bridge, we have very, very different talent sets and very, very different focal areas between Germany and the US, in that Germany is quite focused on replacing their baseload power capabilities. They turned off their entire fission ecosystem in the mid-teens, and they've suffered for it. Given things that are happening with Russia, given things that are happening with energy prices in Europe, there is a lot of will in Germany towards a solution that would provide baseload power, and there's a lot of push towards fusion. And similarly in the US, the US, given the history of our physics expertise, has some of the best scientific minds and engineering minds to build laser fusion programs, to really do the scientific de-risking, and to build the laser development for that technology set that we're going to need as well. So I do think that while it's a bit of a challenge to be a transatlantic company, the advantages in very rarefied ecosystems are pretty profound.
Scott, we got to add just a couple energy nerd technical questions since you hinted at them. You can hopefully wrap these all together. You mentioned LCOE, so you have some target in mind, which is great, starting there, working backwards. That implies you also highlighted baseload. So this is not going to be ramping. You want to run it at super high capacity factor, largely like traditional fission reactors today. Do you have a dominant size of plant, and can you confirm sort of a capacity factor and LCOE that you're looking for?
Yes. So architecturally, when we look at our system, our first generation systems are constrained by target chamber size, like I said prior a little bit. We really need the target chamber to be large enough to keep essentially the heat away from the walls, so that the 150 million degree target at the center is at a material science friendly temperature by the time it hits the walls, but still hot enough to create enough energy to move through the system effectively. What that means for us is that we're looking at building systems that provide about a gigawatt of energy out, from about 2 gigawatts of fusion energy at the target. And when we think about building baseload power, that's about the size that replaces a single core of a fission reactor. So if you were to look at fission architectures that might need to be replaced over the next 20 or 30 years, you could really map out each individual fission core for some of these larger baseload power plants and say, okay, that might be a perfect one-for-one replacement for fusion. And the other thing is, we think about this from a grid capacity, and one of the things that's most important to my view as kind of a infrastructure resilience nerd, building electric car charging. You want electric car charging stations to be 99.9% reliable because they're providing transportation fuel. Similarly with fusion, this is providing baseload power. It needs to be 99.9% reliable. It needs to be up and running all the time. And one of the profound benefits of our approach is that by using these arrays of modular lasers, you can almost envision our system like a data center server rack, where each of these laser beam lines is an individual server. And if a piece of hardware goes down, if a laser beam goes down, you can pull that laser beam out without turning the facility off in hot operation. So the idea of designing for serviceability and designing for resilience, I think, is incredibly important as we're looking at fusion schemes, not just to prove the science of can we see energy gain, but the commercialization capability of developing a system that can be a full baseload reliable, integrated with the grid system.
Mm-hmm. And last one for sure, efficiency, because you mentioned 2 gigawatts of fusion energy. That's the thermal energy, gets you to 1 gigawatt of electrical, and that's largely driven by just the efficiency of boiling water. Did I hear that right?
Correct. So as you go from kind of heat transfer into steam, into systems that look very similar to other baseload energy configurations, it's about a 50% loss, I think, as a very rule of thumb.
And just to complete that cycle, so you would have, using that example, 500 megawatts of energy in to start the lasers, 2 gigawatts of energy out from the thermal reaction, and then 1 gigawatt of electric energy out. So you would be, what's the balance of energy in to energy out at the end of the day in your target plant?
Yeah. So from our target projections, we have what I would consider our conservative projections for the pilot plant and for first gen. And then we have what we think is likely feasible. So when we think about energy gain from our standpoint, the target that we've set for the pilot plant is a gain of 25. The target gain that we're looking at for the first generation commercial power plants is a gain north of 75. And that's based on growth in laser energies, both laser and target efficiency. But if you look at the lasers that are used to power NIF, they use lamps, flash lamps. So they're analog systems. They're about 0.5% energy efficient. What we need to move to is a solid state system. So using diodes rather than flash lamps. Those diodes exist today. They're out in market. They're in laser systems. They just are. It's a different program than using flash lamps. But if you look at laser systems, the lasers that we're looking at are between 10 and 15% energy efficient. So it's quite a different efficiency parameter from a laser perspective than what's being done today. That's probably one of the biggest system shifts. That's one of the most clear, is that for NIF really having a gain of 2.4 and a scientific gain of 1, if you start to move from flash lamp lasers to diode lasers, you go from that 0.5% energy efficient to energy efficiency in the mid-teens.
Great. Well, Scott, I would clearly love to continue to ask you all sorts of nerdy and nuanced questions, but we're out of time, and you've given us a tremendous tour of a different side of fusion, and really appreciated the very commercial, tactical, working backwards from commercial operations. And that's different than the language we've heard described fusion in previously. So really appreciate your perspective here as a non-scientist, but like you said, a 15-year journey of commercialization. This won't be your first one. So Scott, thank you so much for talking with us today.
Thank you, Jeff. Appreciate it. So thank you, guys.
For our audience, we hope you've enjoyed this episode. We always love talking fusion. We're getting more and more episodes on fusion. I think we want to understand what the opportunities are and what's coming our way. If you want to find out more, check out Focused Energy. You want to find out, we want to find out. We're looking forward to having Scott. We hope to have you back in the future and get some progress updates. Thank you again for being on the podcast. For our audience, hope you enjoyed this content. Don't forget to subscribe, follow us on our YouTube channel, and we'll see you again next time on the Insider's Guide to Energy. Bye for now.